For decades, engineers believed that optimization, finding the single best solution among billions of possibilities, was a problem only machines could truly handle. Algorithms, data-driven models, and supercomputers became the heroes of the technological world. But in the shadows of deep caves, in places humans rarely dare to enter, a creature far smaller and far older than any computer was quietly outperforming us. A creature with no eyes tuned for detail, no silicon processors, no programming, yet capable of solving incredibly complex problems faster than modern AI. This creature is the bat. When scientists first studied bats, they were fascinated by the idea of echolocation, the ability to see through sound. But what they didn't realize was that echolocation is more than sensory navigation. It's a built-in optimization engine. Every tiny chirp a bat sends into the world is not simply a signal, it's a calculation. Every returning echo is not just sound, it's data. And the way a bat processes that data is more sophisticated than anyone imagined. A single bat can navigate a chaotic, obstacle-filled cave in complete darkness, chase a moving insect that changes direction dozens of times per second, avoid collisions with other bats, account for wind, humidity, air pressure, and motion, and still use less energy than a simple lead bulb. There is no lag, no hesitation, no overthinking, just perfect, instantaneous decision-making. For humans, creating a machine with that kind of precision takes thousands of lines of code and a processor burning through electricity. For bats, it's natural, automatic, effortless. For years, the scientific community thought they understood this behavior. Bats chirp, the sound bounces, they interpret it, they fly. Simple. But in 2010, something happened that shook the foundations of AI research. A researcher named Xinxi Yang at Cambridge University began examining the patterns behind bat behavior. He didn't just study their biology or their acoustics. He studied their decisions. Why do bats change the frequency of their calls at certain moments? Why do they adjust volume? Why do they alternate between wide, exploratory scans and precise, narrow target scans? Why do their pulses increase when they get closer to prey? What he discovered was staggering. Bats were not acting randomly. They were optimizing constantly. They were performing a type of natural computation so efficient that it made some human algorithms look clumsy by comparison. Yang realized that behind every movement and every chirp, there was a formula, a strategy shaped by millions of years of evolution. Bats had already solved one of the hardest problems in AI. How do you search for the best solution in a massive, chaotic, ever-changing environment without getting stuck, lost, or overwhelmed? In AI, this is called the optimization problem, and it appears in almost every field: engineering, finance, robotics, neuroscience, logistics, and even climate prediction. Humans build complex algorithms to solve these problems, often requiring huge computational power. Bats do it with sound. And so Yang did something brilliant. He translated the behaviors of bats into mathematical rules: how they explore widely when they know nothing, how they refine their search when closing in on a target, how they reduce noise to focus on critical data, how they switch strategies instantly when the environment changes. He turned these rules into a completely new type of algorithm, something he called the bat algorithm. At first, the scientific community didn't believe it. How could a simple animal outperform sophisticated computational models? But tests didn't lie. The bat algorithm quickly proved itself. It began solving optimization problems faster than older, established algorithms. In some cases, it required fewer iterations. In others, it avoided false solutions that trapped traditional AI. And most importantly, it produced consistent results with less computational energy. This was nature's elegance at work. Nature does not waste energy. Nature does not overcomplicate. Nature finds the simplest path that works, and bats were the perfect example. The algorithm mimicked three fundamental bat behaviors. First, frequency tuning. Bats switch between high-frequency calls to gain detail and lower frequencies to scan broadly. In the algorithm, this became a mechanism for exploring big possibilities first, and then sharpening focus when needed. Second, loudness control. Bats reduce their volume the closer they get to their target. This inspired the algorithm to gradually reduce randomness, becoming more stable as it approached a solution. Third, pulse emission rate. As bats near prey, they increase the rate of their chirps, allowing faster sampling of their surroundings. The algorithm mirrored this by increasing solution accuracy near optimal results. These three simple behaviors created a shockwave in engineering fields. Suddenly, antenna designers found better configurations. Drone navigation systems improved. Medical imaging became more precise. Wireless communication networks optimized signal flow. Earthquake prediction models enhanced their accuracy. Even robotic control systems began borrowing from bat-inspired strategies. And yet, the most astonishing revelation was this. Even after building a mathematical model of bat behavior, even after copying their strategies into code, AI still couldn't match a real bat. Because a bat's intelligence isn't just in its brain. It's in its skin, its ears, its wings, the vibrations in the air, the structure of its skull, even its tiny hairs that detect shifts in wind patterns. A bat's decision-making system is a fusion of biological sensors working together in ways machines still struggle to replicate. When a bat hunts, it processes information in parallel, simultaneously integrating sound, echo delay, Doppler shift, wing feedback, environmental geometry, and swarm dynamics. A human-made sensor system would require dozens of specialized components to achieve the same sensory richness, and even then, it would be slower. Nature doesn't rely on raw computing power. It relies on elegant feedback loops, efficiency, and simplicity. Perhaps the most fascinating thing is that bats are not even trying to optimize. They're simply trying to survive. Their problem-solving ability is a side effect of evolution, an accidental brilliance that humans are only now beginning to understand. But the story goes deeper. When scientists placed bats in experimental tunnels with microphones, high-speed cameras, and motion tracking systems, they observed something that changed everything. A bat doesn't navigate by building a mental map of its environment the way humans do. It doesn't see a cave. It doesn't visualize shapes. It doesn't even reconstruct objects. Instead, bats live in a world of abstract information, patterns of echoes representing movement, density, and disturbance. In other words, they don't overthink. They don't get stuck trying to make sense of everything at once. They take in only the information they need and discard the rest. This is the part that fascinated AI researchers the most, because modern AI has the opposite problem: too much information. AI models often drown in data, overfit, or hallucinate patterns that don't exist. Bats, on the other hand, master the art of ignoring, filtering noise with unbelievable precision. This ability, this selective attention, is what gives them their superpower. While flying through a swarm of hundreds of other bats, each emitting loud calls, a bat somehow isolates its own echoes. It's like trying to hear your own voice in a stadium of shouting people. Yet bats do it flawlessly. They can detect the faint flutter of a moth wing between dozens of competing signals. They can determine distance down to less than a millimeter, direction down to less than a degree, and motion down to a fraction of a millisecond. Their precision rivals some military-grade sonar systems. And even stranger, different species of bats use different strategies. Some use frequency modulation. Some use constant frequency. Some use harmonics to refine targets. Some emit calls that humans can't detect even with specialized equipment. Each species is like a different algorithm, evolved for different environments and challenges. This diversity inspired even more innovation in computing. Engineers began combining ideas from different bats to create hybrid models that could search better than traditional algorithms. Researchers discovered that bat-inspired algorithms were especially powerful in chaotic environments, places with shifting variables, changing targets, and incomplete data. The same conditions bats experience nightly. Today, as AI becomes increasingly complex, the lessons from bats have become even more valuable. Their approach shows that intelligence isn't just raw power, it's elegance, minimalism, efficiency, the ability to balance exploration with precision, the ability to adapt instantly when the environment changes, the ability to optimize without overcomplicating. Some scientists even believe that studying bats could lead to breakthroughs in autonomous vehicles, swarming drones, earthquake mapping, biomedical sensors, and even the optimization of neural networks themselves. Imagine self-driving cars that navigate based on dynamic acoustic mapping instead of camera-based systems. Imagine drones communicating like bat swarms, avoiding collisions with natural precision. Imagine tiny robots exploring collapsed buildings using pulse-based mapping inspired by echolocation. These possibilities are not science fiction. They're already being tested. And yet, despite all this progress, something remains untouched. Something AI still can't replicate. Something even the most advanced algorithms struggle to imitate. The pure artistry of how bats integrate information in real time, instantly, intuitively, flawlessly. They calculate without calculating. They solve without solving. They simply do. Nature's elegance is not just intelligence, it is harmony. Every time we build a new algorithm based on animals, we are reminded that humanity is still a student. We observe, we copy, and we learn. But nature had millions of years to refine what we now call technology. And often, the answers to our most complicated problems have already been solved, not in a lab, not in a computer, but in the beating wings of creatures who fly through darkness as if it were daylight. Humans built artificial intelligence, but bats built something else, natural intelligence. Silent, efficient, and frighteningly effective. And so we return to the same question that fascinates every engineer who studies nature's designs. If a bird can redesign a bullet train, if a termite can solve air conditioning, if a slime mold can map a subway system, and if a bat can outperform modern algorithms, then what else is nature hiding? What ancient secrets are still waiting to be discovered? Maybe the next great AI breakthrough won't come from a supercomputer or a research lab. Maybe it will come from a small creature hanging upside down in a quiet cave, calculating the world with nothing but sound.